So, happy Thursday, everybody. I think we have everybody in the classroom that we're supposed to have. It's kind of interesting. So we are going to get started. First thing we're going to do is look in the WebEx chat. Come on. Oh. There we go. So I'm going to look at the next chat. So we haven't already told and have a quick conversation with them about how high your box is and what your other dimensions are and what your final volume is, okay? And then when you've got your final volume, I'm going to start a thread here. Volume, data collection. Go ahead and reply that thread with your height and your volume numbers. So I'm going to give you a minute or two to do that. So we're all going to have to be on WebEx. And while you're there, you might as well log into Blackboard because you're going to need a link in just a minute.
So we're just responding to your WebEx chat with our volume.
Okay, so yeah, with the height and the volume. Okay. So I'm just monitoring the WebEx chat right now, just watching the data come in. If you have that data, once you've talked to your partner, then you're going to go into Blackboard Unit 5, Day 15, and you're going to click the link for the Google Sheet. Filling out a Google Sheet together. I'm going to turn my video because I think it's making my screen here. So I'm going to stop my video. It makes it a little bit smoother for me to navigate my screen. So what you should be seeing is the chat. That looks good, Tom. Yeah, height of this, volume of this. Okay. So what you're looking at on my screen here is my Blackboard thing, and I have this link right here under day 15, this link that says data collection for maximizing volume. That's what you should click. And then you can go ahead and put in your volume in the yellow highlighted cells. Yeah. Dang it. I meant to change it. Rats. Let me change it right now. Well, you only. No. Why am I you only? Why am I signed out? Right? Verify it's you. It is me. Doesn't like me today either. Okay, let me hold on. File. Where is it? Share. Change. Anyone with a link. It doesn't. Oh, view only. No. Edit. That's what I want. Okay, now you should be able to edit it. So we're going to watch the data. I'm watching the data come in on 2 screens now. It's, oh, let me go back there. In Blackboard, Unit 5, right, where we find all our materials. So in Blackboard, Unit 5, day 15, it kind of looks like that, although you probably see the videos because of your student account. And then it's right here. I'll put my cursor right next to it. No problem. Anybody, Krista, do you need tape for your box or anything like that? Oh, okay, yeah, that happens. Okay, so I am gonna switch over. I'm just gonna switch over to the spreadsheet. If you need that link, it's in Blackboard. If you don't know where it is, that's okay. Just give me a holler. Team Gonzalez, I don't see your information in WebEx. It's underlined. Oh, could you recalculate Team Gonzalez? That's a little bit high. I'm gonna do this. That's too big. I'll give you a hint. You're oh no, that's too big. Something happened there. Your height is not 7. It might be 7 boxes, but your height is not 7. Oh, yeah, just numbers, because I have the unit up above here. Yeah, because we need to evaluate this data. So we got to just have numbers. Yeah. Yeah, good question. Yeah, you notice in your notes, you've got this table and this graph. Okay, so you can start putting those in your notes if you want to. We will get to a notes page though. Just a fair warning. Okay. So, okay, Jalen and Hannah, now yours is fine. Yep. Jason Kelly, now yours is fine. Okay, where's Batten Radonsky? All right, so we've got all our values here. They look good. Just waiting on Summel's and Caleb's to go into the spreadsheet. I'm just looking for it in the data here too. I don't see the calculation. Okay, so these look good. So before we jump into notes, we got to talk about the top point and the bottom point. And then we'll let Summel and Caleb get their value into their box as we talk about this. So what happens if I have a height of 0? What does that mean? I don't have a box, right? In other words, I didn't cut anything out, so I can't fold anything up. So if that's the case, what volume do I have? I got 0 volume, so I'm going to put that in. There we go. That gives me a point down there at the origin. Now, what if I cut out 5 inches? This is kind of a tougher one to conceptualize. Yeah, I would cut completely through that 10-inch width. If I cut 5 inches in on a side, I've cut that 10-inch width completely through. So I still have no box, which means I have, again, 0 volume. Okay, that's because of the constraint of our piece of paper, right? We all started with a 12 by 10-inch piece of paper, and there's a point at which where if you cut enough off, you won't have any flaps on that 10-inch side anymore. Okay. So there's our data. Now we're missing a data point here at 0.5. We really want that data point. So Samuel, and you guys are here. I know you're here. I see you. I see you're here, Samuel, and who am I looking for? Radonsky. Yep, you're both here. So I need your data. You guys have that? Samuel, you there? Caleb?
Trying to figure it out right now.
Okay, what are you stuck on? We can walk you through it. You guys are going to turn up how many boxes?
Is it 52.5?
No. Yeah, you're thinking it's symmetrical, right? It's not, but you have a 1/2 inch height. How many boxes is that? How many boxes do you have turned up on your model? Okay, so either Caleb or Samil, take a picture of your box and send it in WebEx. Let's see what this looks like. All right, you guys work on that. I want to pick in about in the next minute or so. I'm going to keep talking. Okay, so looking at this data, we know that we should have another data point in here, but if we look at this data here, can you speculate what sort of function that is? Maybe a parabola, right? Okay, let's try it. So if I come over here, come on, there we go. And I get into here, I can do a fit. There's a line, definitely not linear, right? Okay, but I can come down and tweak this parabola. Okay, so parabola is a polynomial, right? It's an x squared. So let's try an x squared. There's a parabola. Exactly. So now we start trying higher level polynomials. So we're going to try an x cubed. That looks really good. And we'll find out from Samel and Caleb in a minute that their point is going to be just under 50. Okay, if we can kind of speculate that there. Because you know, 1/2 is about right here. It's not exactly 50, but it's just under 50. So guys, let me know when you have that number or that pick. So we know we have some sort of x cubed function. Now think about that. We're talking about the volume of a box, right? And we calculate the volume of the box by doing what calculation? Length times width times height. So let's take the extreme, let's call it a cube, right? It would be x times x times x or x cubed, right? This is not exactly x cubed because we know x cubed looks different. But it's got to be some sort of 3rd degree polynomial just because of the constraints. We're talking about the physical volume of a box. So far, so good? Okay, so what is this? What is this function specifically? Google Sheets doesn't have the capability of evaluating it like your calculator would. Okay, so we need to look at this analytically. Alrighty, so we're going to start the notes now. If you haven't already, oopsies, if you haven't already gotten the data in, that's what we're going to do right now. So at least get the table in there. Okay, and there we go. At least get your data into the table. I'm just trying to, there we go. I'm trying to show both things here, which is not exactly convenient, but we'll get it to work here. There we go. Okay, so put your data in. And this area was for your specific work. If you want to put your work in there, you can. Not a big deal if you don't have it in there. Okay. But we need to do some we need to do some analytical evaluation here. Okay, in fact, we're going to skip that. So we're going to look at this analytically. Okay, so this is what we do when we don't have a calculator. We have to look at this box and we have to look at what we're trying to create physically and then what constraints we have. Okay, so we know that we're trying to maximize the volume of a box. And so we know that we are going to have to somehow maximize the function for the volume of the box, right? So, and we know the volume of the box is length times width times height. So we know this is the height. And here's the constraint. The constraint is that we all started with a 10-inch by 12-inch piece of paper. And so depending upon how much we folded up, we were left with a length and a width that was different than other people's lengths and widths. Does that make sense? Okay, so those lengths and widths are dependent upon the height of the box because of that constraint. Does that make sense? If you had a tiny height, then you had a big length and width. If you had a big height, then you had a tiny length and width. Okay, so how is that related? Well, if we call this H, which means this is H and this is H, and that's true on all of these corners, then if this whole width was 10 inches and we cut H out of each side, how long does that make this flap? The 10-inch width, 10 minus 2H, exactly, right? And so that width then and that length are going to be functions of H. So that width is 10 minus 2H. Now let's look at this 12-inch rectangle that we started with. If this thing was 12 inches and I notch out H on the top and the H on the bottom, what does it leave this tab to be? 12 minus 2H. And then when we fold those up, this becomes the width and this becomes the length. So we now have a model where we can say, hey, I can take out these extra variables, L and W, and I can replace them with something that's a function of H. So now I have a single variable, one variable to differentiate, which is a lot easier than differentiating 3 variables and doing a bunch of chain rules. Excuse me, a bunch of product rules and chain rules, really. Any questions so far? So far, so good? Okay, so let me just jump back for a second here because we should be able to do this. This is what I have these other columns for. That's our theoretical model. Right? That's if everybody folded everything perfectly, right? So I'm going to put that theoretical model into here. So it is, let's see, 12 minus 2H. So this equals 12 minus 2 times my height, which is this cell, times 10 minus 2 times my height again, times my height. Okay, and I'm going to autofill that. There we go. Look at those, look at the data we got compared to the data we calculated by measuring. I wish I could just do a curve fit and have it spit out a formula at you, but Google Sheets doesn't allow me to do that. The data matches exactly. So Mel and Caleb, here's your answer. 49.5. Okay. 49.5. Look at how that dot fits in real good, right on the model. Okay, so this model like I said, I wish Google Sheets would give me that equation of that curve it puts in there, but it doesn't. This curve must be this function because I put this function in over here and I got the numbers to match exactly. Okay, so we know that this is the model, and we need to maximize that, which means we need to find this hill. Does that make sense? We need to find that hill. Well, how do we find that hill? Well, yeah, and there's two really probably common ways to find that hill. Yeah, do you have one way? We don't like to use trace though. We're gonna use calc.
Okay.
What are you gonna calculate? Yes, exactly. We can put that function in our calculator and do a second calc maximum. Okay. We could also do what? Exactly. That's not. Yeah, table's not good enough. We need this, which is why tracing is not good enough either. What do we do with calculus to find that maximum? What occurs at the maximum? Slope of 0. So what we can do is that if I do a second calc maximum, this is the answer it's going to give me. Okay. And so what we have here, and this table is part of the candidates test, is that our constraints say we can't have a height of 0 and we can't have a height of 5, but we can have all the heights in between. And our maximum height is at 1.811 inches. And that gives us a maximum value. I said maximum height, I meant just height. That gives us a maximum value of 96.771 cubic inches. Okay. So trying to find the right icon here. There we go. If I pull up my graphing calculator, which is here somewhere, there it is. If I pull up my graphing calculator and I put this function in, because we're recording this, I'm going to do this calc max, so that we have a resource to go find a calc max, because it's a very important skill in a calculator. Wish I would have loaded the calculator before the class. Calculator. There it is. So if you have your graphing calculator, what you're going to do is you're going to go on to the y1, you're going to start putting in that function. Close that. I'm going to turn off my plots because that's always problematic when you're trying to graph a function. All right, so I'm going to go ahead and put in 12 minus 2, but I got to use x because that's my variable in my calculator. We don't have h's. I mean, we do, but we don't use them. The calculator doesn't recognize that as a variable. 10 minus 2x times x. And then I'm going to set my window because I know my numbers. I'm going to set my window from 0 to 5 because that's my constraint. And I'm going to graph this. And there is our function. And now second calc. Calc and trace are the same thing. It's just that calc is smarter. Okay. Second calc maximum is a 4. And now I got to give it a domain in this area. So I'm going to back off until I get before the hill. And that's going to be my left bound. So I'm going to hit enter. And then I'm going to go forward until I'm after the hill. And that's going to be my right bound. And I'm going to hit enter. And I'm going to guess. You can really just guess from right there. I'll back off a little bit. I'm going to give it a guess. And it's going to come up with a 1.811, rounded to 3 decimal places, 96.771, again rounded. Okay? The questions about that?
One.
Okay? Yeah.
How would you know that your constraints are 0 to 5 without the graph earlier?
Because if we look at the physical size of the piece of paper, it's 10 by 12. That make sense?
Yeah.
Okay, now let's pretend that my H is 0. If my H is 0, that means I don't have a notch here and I don't have flaps to cut out. Does that make sense?
Yeah.
Okay, let's say my H is 5. If my H is 5, that means I'm cutting out 5 inches, means I'm going all the way to the middle of my width. And then I'm coming over here and going all the way to the middle of my width, and I just lost my tab on the top.
I see. Okay. That makes more sense then.
Yeah, so long story short, you look at the short dimension and you cut it in half, and that's your constraint.
All right.
Because that's the tab that's going to disappear first.
All right. That makes more sense then. Thank you.
No problem. Okay, so going on then, you know, this is what we're doing, right? We are cutting those tabs off and folding them up. We're cutting the corners off, excuse me, and folding it up and making that open top box. It can be open to the top volume, right? And the top doesn't have anything to do with the volume. So, so the idea then is here's our strategy for solving these optimization problems. Is really geared toward calculator. We're going to write for the quantity we want to optimize. In this case, it was volume. We use constraints to express the relationships. That's how we got the 10 minus 2h and the 12 minus 2h, because the 10 by 12 is our constraint. And then we rewrote our volume in terms of single variable. And here's the no calculator part. Okay, yes, we can just do a second calc max if we have a calculator. There's no reason to put in any calculus whatsoever if you have a calculator, because you can do this without a calculus. That's why they do, because sometimes they do optimizing in pre-calc, because they do it all on a calculator. But if you don't have a calculator, then we got to differentiate so we can find that max, that hill, or that valley. Maybe it's a minimum question, like minimizing surface area. But we got to find that, and then we've got to set it equal to 0, because we know set is equal to 0. The derivative is equal to 0, and then we have to interpret our answer, and that comes back to doing that candidates test, confirming that yep, this is in fact the minimum because those constraint points are higher, or in this case back to maximum because the volume x rates at 0 and 5 is 0. Okay, we doing okay so far? All right, so let's take a look at this example here, and I've changed the example a little bit so that we can do something without a calculator to kind of show you how this process works. So that's where the calculus is used. So in this example, we can make a box the same way, but this time the base has to be square. Okay, so in other words, we have to start with a square piece of paper in order to make a square base. Okay, so we need to design an open top box with a square base, and it has to hold a volume of exactly 32 cubic inches. So that is my constraint. That's my limiting factor, is I have to have a volume of exactly 32 inches. What is the minimum possible surface area needed? Right, so in this situation, we are going to minimize surface area. So this might be an application that Amazon might do so that they can minimize the amount of cardboard they need to make boxes, that sort of thing. Okay, so Here's our constraint. Yeah, come. 5. Yeah, so it's not quite realistic, right? Amazon wouldn't use exactly this model because they need it. They would use a different net to create the box. That would be a little more complicated. Okay, so it has to hold a volume of exactly 32 cubic inches. So we know the base has to be square. So we know since those are our constraints, since we have a square base, we are going to call it x by x, minimizing the number of variables we need. No longer L times W. Okay, and we have this height here. We don't know what the height needs to be though, but so we do have to introduce this second variable here. So at this point, we can calculate the surface area. So we're going to have a bottom and we're going to have 4 sides. And the bottom is going to be x squared, and each side is going to be x long and h high. So our surface area is going to be 4 sides, 4x times h plus x squared. So there's our model. That's not in terms of one variable yet, though, right? We still have 2 variables in there. So we're going to use this other constraint so that we can get the h out of there and have an x in there. And we know that volume is length times width times height. So we're going to use that. Volume is length times width times height. The length and the width are x and x. And the volume, we know we're going to pin that volume down at 32. So we know that h is equal to 32 over x squared. That makes sense? So we're going to take that and substitute it in so that we can get our optimizing equation in terms of a single variable. Okay, so we're going to do that. And then I'm going to simplify that. 4 times 32 is 128. X over x squared, I'm going to cancel one of the x squareds on the bottom. And I have that. That's what I have to differentiate. Am I going too fast? You're doing okay? Doing okay? Okay. So remember when you differentiate that the 128 over x looks like this, right? 128 x to the minus 1 plus x squared. This is really popular when we talk about surface area. We're going to have an x to the minus 1 to differentiate. Okay. We haven't differentiated yet, right? We just rewrote the fraction as something to a negative exponent. Okay, so now we're going to do the calculus. Haven't done it yet. We're going to bring down negative 1, make a negative 128 x to the minus 2, and then plus 2x. Right, differentiate each term. That's my derivative. I want to minimize this, so I'm looking for my derivative is equal to 0. Okay, so here's my derivative, setting it to 0, because I want to find that value. Yeah. So this might look really intimidating because of the negative power, but remember, it's just that. And that is a lot more palatable to solve, because I'm going to take the 2x to the right-hand side, and I'm going to do a cross multiply, set them equal to each other. I might have taken this to the other side to make it positive, but let's see what I do here. Yep, that's what I did. Okay, now I can cross multiply. So remember, this is 2x is 2x divided by 1. That's what it means, one in the denominator. So I end up with 2x cubed equals 128. That's my cross multiply. Okay, divide out the 2. X cubed is 64. Remember, you don't have a calculator. You can't take the cube root of 64. In your brain, you have to think, what times what is 64? 4 times 4 times 4. They might give you something like that. It won't be difficult. So we know we need a 4 by 4 box. You did okay? Okay, so it's asking you, what is the surface area? So we got to put 4 back in there. That's the question you have to answer. Because it's not asking you what should the dimensions be, it's saying, what is the surface area? We know the surface area should be 48 square inches. Okay, that's what the surface area of our box is. Doing okay? Okay. You've got 2 more examples that we're going to do. I'm going to put those in as notes for tomorrow. Okay, so that you can come in and then you can work on the topic questions right from the get-go at the beginning of class. So look for those as you're taking your notes tonight. And there's just one con and no new con tomorrow. So it's just the one con assignment. Okay, any questions? That went better than I thought it would. No, sometimes, you know, when you do like on Monday, we're gonna still do optimizing tomorrow, that's gonna be great. I'm sorry. You know what I'm saying? Well, I bet you can have the questions and probably the Congress tomorrow. Yes. Have a good Thursday, everybody.
Hey, Miss Potter, are you still there?
I'm still here.